Hello my friends and welcome back to the Today Machine channel. Disc formation. The process begins with pressing the steel to give the central disc a concave shape, followed by the creation of various openings. A large central hole is formed, surrounded by smaller ones, known as windows, which aid in brake cooling. Rings are then applied to the windows through a process called coining, enhancing both aesthetics and durability. At first glance, racing wheels might seem similar to regular ones, but they feature distinct shapes and angles that make them unique. These wheels are designed to withstand extreme speeds and provide stability during sharp turns. The production process ensures the highest reliability and performance, starting with the use of low-alloy steel, a robust material. Ring and disc assembly. A smaller press shapes the mounting holes, allowing the disc to be fixed onto the vehicle. Afterward, the disc undergoes meticulous finishing and is combined with the rim. The rim starts as rolled steel, which is flattened, cut to size, and stamped with a trademark. The steel is then divided into 3 coils, used to create rings. Rim shaping. These rings are welded, trimmed, and subjected to heavy pressing to form the flanges. This shaping forms the rim seat, where the tire is mounted. The edges are polished to ensure smoothness. Final assembly. The disc and rim are joined by heating the rim, allowing the disc to fit snugly as the rim cools. Welding solidifies this bond. A threaded hole for the valve is drilled and reinforced. Finally, a yellow stripe and serial number are applied for identification. The result is a high-performance steel wheel, ready to tackle the demands of competitive racing with precision and strength. Inspection and initial preparation. Inspection. Begin by thoroughly inspecting the tire for visible damage, punctures, or other injuries. Proper evaluation ensures that the repair method and materials chosen match the type and extent of damage. Skive the damaged area. Carefully skive, cut and remove the damaged section of the tire to expose the injury fully. Ensure the injury is clear of obstructions and irregularities. Inspect the injury. Assess the injury depth and extent again to confirm the repair feasibility and select the appropriate repair unit. Buff the skived area. Buff the skived surface using a wire brush or specialized buffing tool to create a clean and textured surface that enhances adhesion. Taper the skive. Taper the skive to an angle of 30 to 45 degrees, ensuring a smooth transition for the repair material to bond effectively. Buff the injury channel. Buff the channel of the injury to remove debris and create a uniform texture inside the damaged area. Clean the area. Remove all buffing debris with a vacuum or cleaning tool. A clean surface ensures optimal bonding of repair components. Repair unit selection and preparation. Choose the proper repair unit. Select the appropriate repair unit based on the type and size of the injury. Options include GTR radial repair units for radial tires or OTR bias repair units for bias ply tires. Mark the center line. Mark a center line across the injury for accurate alignment of the repair unit. Outline the repair unit. Position the repair unit over the injury and outline it. Create an additional outline approximately 1 inch smaller than the repair unit to define the bonding area. Advanced skiving and buffing. Skive through the inner liner and plies. Skive through the inner liner and 2 plies, tapering the skive to an angle of 60 degrees from the inner liner to the middle line. This step ensures deep penetration of the repair material. Buff the skive area. Buff to the outer line, creating a rough surface for optimal adhesion. Wire brush buffed areas. Use a wire brush to refine the buffed areas, ensuring an even texture. Cement application. Apply cement. First coat. Apply the first coat of cement to the buffed area. Allow it to dry thoroughly. Recheck injury size. Verify the injury dimensions again to ensure consistency with the repair plan. Vent the skived area. Ventilate the skived area to prevent air entrapment during repair. Apply cement. Second coat. Apply a second coat of cement, ensuring even coverage. Repair unit installation. Remove poly backing. Peel off the poly backing from the repair unit. Position and stitch repair unit. Place the repair unit over the injury, aligning it with the center line. Off the road, OTR, tires are essential in heavy industries such as mining, construction, and agriculture, where robust performance is critical under extreme conditions. REMA Tip Top, a leader in tire repair solutions, provides advanced materials and procedures to ensure the durability and efficiency of OTR tire repairs. The process includes using GTR radial repair units, GTR basket radial repair units, OTR bias repair units, OTR basket bias repair units, sub-tread bias repair units, and essential accessories like cements and cushion gums. This guide details the comprehensive steps to repair OTR tires effectively. Stitch thoroughly to ensure the unit bonds securely to the tire surface. Filling and finishing. Fill the skive with cushion gum. Apply cushion gum to the tapered skive area and stitch thoroughly to create a smooth, filled surface. Line the skive. Line the skive with an additional layer of cushion gum and stitch it thoroughly to reinforce the repair. Trim excess material. Trim any excess cushion gum or rubber to ensure a clean and professional finish. Cement and strip edges. Apply cement to the outer edge of the repair unit and strip the edges with cushion gum for a seamless finish. Stitch edges. Stitch the edges of the cushion gum to secure the repair unit firmly in place. Final steps. Inspect the repair. Perform a thorough inspection to ensure all steps have been executed properly and the repair unit is securely bonded. Test the tire. Test the repaired tire under controlled conditions to confirm its durability and readiness for heavy-duty applications. The tire sidewall cutter machine is designed to efficiently cut the sidewalls of tires, preparing them for recycling or repurposing. The process begins with securely positioning the tire onto the machine's cutting platform. Using a powerful and precise blade system, the machine slices through the sidewalls with ease. In the video, the machine demonstrates cutting a 12R24 tire, a large-size truck tire. The operation is smooth and consistent, ensuring minimal waste and maximum precision. This machine is ideal for processing various tire sizes, contributing to eco-friendly disposal and recycling practices by simplifying the separation of sidewalls from the tread. The production process of Ibenstock core drill machines reflects a commitment to precision, innovation, and quality. Established in Germany in 1919, the company designs and manufactures professional-grade power tools, with an impressive 80% of parts produced in-house. This includes motor and gearbox housings, protective covers, and other components, ensuring superior control over quality and durability. Key processes such as casting and powder coating are conducted on-site in the Erzgebirge region, leveraging advanced CAD systems and CNC machining centers. These tools enable the development team to translate creative ideas into innovative products efficiently. The company's high level of vertical integration allows for direct influence over production quality and swift adaptation to market changes, ensuring continuous improvement of their tools. The adherence to the DIN and ISO 9001-2015 standard underlines the comprehensive quality management system implemented at Ibenstock. The robustness and durability of these machines make them indispensable for demanding construction site applications. A generator stator rewind restores efficiency and extends the life of power generation equipment. The process begins with bar removal, carefully extracting the old stator bars to prevent core damage. Next, core cleaning ensures the removal of contaminants, enhancing the core's insulation and performance. A high potential test is conducted to verify the core's electrical integrity before proceeding. Bar installation involves inserting new stator bars with precision, followed by bar tying and brazing to secure them and establish reliable electrical connections. Insulating caps are applied to protect bar ends from wear and electrical stress. The next step, installing blocking, stabilizes the winding structure. During wet tying, resin-impregnated materials are applied to secure components. Finally, electrical testing confirms that the rewind process meets performance and safety standards, ensuring the generator operates efficiently and reliably under load conditions. Wärtsilä's marine diesel engines are engineered to deliver reliability, optimal power, and fuel efficiency for marine applications. The machining process for these advanced engines involves precision engineering to ensure durability and performance. Starting with high-grade materials, the components undergo CNC machining to achieve exact tolerances required for robust operation under harsh marine conditions. Critical parts, such as engine blocks, crankshafts, and cylinder heads, are precision machined using advanced tools and techniques, including boring, honing, and surface grinding. Wärtsilä integrates the latest technologies to enhance fuel economy and reduce emissions, aligning with stringent environmental standards. The machining process emphasizes quality control through continuous monitoring and rigorous testing to ensure safety and easy maintenance. By combining cutting-edge innovation with proven engineering practices, Wärtsilä delivers diesel engines that not only meet but exceed the expectations of the marine industry. Clue's narrow gap weld technology revolutionizes thick plate welding with its MIG/MAG process, offering exceptional efficiency. By reducing weld seam volume by up to 60% compared to traditional methods, it minimizes welding time and material costs for filler, shielding gas, and power. At its core is a rectangular narrow gap blade, up to 400 mm long, which precisely guides the wire electrode, shielding gas, and cooling water. This innovative approach produces consistent, high-quality weld seams while maintaining low energy input. The process is particularly advantageous for steel and high-strength fine-grained structural steel, ensuring superior results with reduced resource consumption. The construction of Ada Nova, the world's first fully LNG-powered cruise ship, involved a highly detailed and multi-stage process at the Meyer WERFT shipyard in Papenburg, Germany. The project began with the keel laying, marking the official start of construction. The first major element was the manufacturing of the machinery room module, a crucial component that houses the ship's complex energy systems, including the dual-fuel hybrid engines capable of running on either LNG or traditional fuel. Following this, the construction continued with the assembly of large structural blocks. The first floating part was constructed, followed by the second floating section, which would eventually form part of the hull. These massive sections were built separately before being merged to form the base structure of the ship. The cabin installation process began next, with thousands of rooms being fitted into place across the ship's 20 decks. Simultaneously, the mounting of the ship's pods, which control the propulsion and maneuvering, took place. The assembly of the propellers followed, contributing to the vessel's power systems. Once the main construction was completed, the ship was floated out of the dry dock in a process known as undocking. The final step was the Ems River transfer, where Ada Nova was moved to the North Sea for its final trials. This transfer marked a key milestone as the ship was readied for delivery. Naviera Petrol, a Peruvian maritime company specializing in the transport of bulk liquid chemicals, undertakes the biannual dry dock maintenance of its chemical tanker, Moquegua, at the SEMA Naval Base in Callao, Peru. This meticulous process is executed following stringent timelines and quality standards to ensure the vessel's optimal performance and reliability. The maintenance begins with the docking of the ship, carefully maneuvered into the dry dock. Once the vessel is secured on its supports, the cleaning phase commences. The ship's hull, often encrusted with marine organisms that can hinder hydrodynamic efficiency and increase fuel consumption, undergoes high-pressure water jetting to remove all buildup. This thorough cleaning prepares the surface for the subsequent abrasive blasting. Abrasive blasting with copper slag removes old, deteriorated paint layers from the hull. This step ensures a smooth surface for the application of new protective coatings. Meanwhile, the ship's mechanical components, including the propulsion shaft, undergo comprehensive maintenance. The propulsion system is entirely disassembled for inspection and repairs, including polishing the propeller and reassembling components with precise adjustments to guarantee efficient operation. The internal systems, such as the hydraulic system critical for ballast and cargo pump operations, are also inspected and maintained. Specialists ensure these systems function seamlessly to support the tanker's demanding operational requirements. Simultaneous tasks occur within the ship's stainless steel tanks, where an expert team examines every inch for signs of rust or wear. Any detected issues are rectified to meet the rigorous standards required for transporting chemicals like sulfuric acid safely. The final stage of maintenance focuses on applying 4 layers of protective coatings. The last layer, a silicone-based paint, prevents the adhesion of marine organisms, adhering to the latest environmental regulations. Once all tasks are complete, the dry dock is flooded, and the Moquegua is refloated, ready to resume operations. Naviera Petrol's commitment to excellence ensures the Moquegua operates at full capacity year-round. This dedication reflects the company's leadership in maritime transport, supported by its skilled workforce and cutting-edge maintenance practices. Offshore wind turbine installation, a technological feat. Offshore wind turbine installation is a complex and highly specialized process aimed at harnessing the vast energy potential of oceanic wind. With offshore wind farms projected to supply 25% of global electricity demand by 2050, this industry is experiencing rapid growth. Recent advancements in turbine size, installation vessels, and foundation designs have significantly boosted efficiency. Turbine size and power output. Modern offshore wind turbines are enormous, with rotor diameters exceeding 220 meters and hub heights surpassing 150 meters. For example, General Electric's Haliade X turbine, a benchmark in the industry, has a capacity of 14 megawatts, enough to power 12,000 homes annually. Offshore wind farms like Dogger Bank in the UK, expected to host 277 turbines, aim to generate 3.6 gigawatts, enough electricity for 6 million homes. Installation challenges and techniques. Installing these turbines requires precision and advanced engineering. The process begins with preparing the seabed and installing foundations, which can be monopiles, jacket foundations, or floating platforms depending on water depth. Monopiles, used in waters up to 40 meters deep, can reach diameters of 10 meters and weigh over 1,500 tons. Floating turbines, suited for depths exceeding 60 meters, are tethered by mooring lines to seabed anchors, enabling deployment in previously inaccessible areas. Vessels and equipment. Installation vessels like the Seajacks Skyla and Voltaire are crucial for transporting and erecting turbine components. These jack-up vessels are equipped with cranes capable of lifting over 3,000 tons, allowing them to handle the largest turbines. In 2023, the Voltaire set a record by installing the first 14 megawatts turbine in Taiwan's Chongfang and Zhaidao wind farm. Cost and time efficiency. Offshore wind installation costs have declined sharply over the past decade, dropping from $120 per megawatt hour in 2010 to under $50 per megawatt hour today. This is largely due to economies of scale and technological innovation. For instance, the time to install a single turbine has decreased from several weeks to about 24 to 48 hours, depending on conditions. Future prospects. The global offshore wind market is expected to grow at a compound annual growth rate, CAGR, of 15.2%, reaching 630 gigawatts by 2050. Regions like Europe lead the charge, with 80 gigawatts already installed, while Asia and the US are rapidly expanding capacity. Floating turbines are predicted to account for 15% of installations by 2035, unlocking new potential in deep water areas. The craft of manual rope splicing is one of the rarest and most demanding professions, requiring exceptional skill, strength, and precision. This is especially true when working with large diameter ropes, such as those measuring 72 millimeters in diameter. Completing a single splice involves threading and interweaving 60 individual strands by hand, a physically taxing and time-intensive process. Each strand must be carefully separated, aligned, and intertwined with others to ensure the rope maintains its structural integrity and can withstand high levels of stress. For a rope of this size and strength, the combined weight of the materials being manipulated during the splicing process can exceed 150 kilograms, adding to the physical challenge. The entire procedure can take upwards of 8 to 10 hours, depending on the complexity of the splice and the experience of the splicer. Precision is critical. Even a minor error can compromise the rope's strength and safety. This level of meticulous craftsmanship is why only a handful of specialists worldwide are skilled enough to perform such work. Manual splicing is not only a testament to human endurance and skill but also vital in industries like shipping, construction, and offshore operations, where ropes of this size are used to secure loads or anchor massive structures. Despite advances in automation, the expertise of a skilled splicer remains irreplaceable for tasks requiring unique customization or repairs in the field. A conventional telescopic single drilling rig connection is a fundamental process in oil and gas drilling operations. It involves the assembly and connection of individual drill pipe sections, typically referred to as singles, to extend the drill string into the wellbore. This process is crucial for drilling deeper into the Earth's subsurface. The telescopic aspect refers to the rig's ability to manage and handle varying lengths of drill pipes with precision. This design feature is especially important when working with limited rig height or when transitioning between different pipe lengths. A telescopic Kelly or top drive system is often utilized to achieve the required connection and alignment. The process begins by hoisting the single drill pipe from the pipe rack using the rig's hoisting system. The pipe is then positioned vertically in the derrick and aligned with the drill string. Once in place, the rotary table or top drive system rotates the pipe to thread it securely to the existing drill string. This connection must be tight and leak-proof to prevent operational hazards. Efficient handling of singles ensures uninterrupted drilling operations, minimizes downtime, and enhances safety. This method remains widely used in the industry for its reliability and simplicity, making it a cornerstone of modern drilling techniques. The Oscoach hydraulic transfer press is an advanced solution for kettle production, streamlining the manufacturing process with precision and efficiency. The system begins with the pre-formed blank or component being positioned on the die, prepared for shaping. Using a powerful hydraulic mechanism, the press applies consistent, high-pressure force to transfer the material into the desired kettle shape. The transfer process ensures uniform thickness, seamless edges, and precise dimensions, meeting stringent quality standards. Advanced control systems allow for customizable settings to accommodate various sizes and designs of kettles, making the press versatile for different production needs. Key features include automated material handling, rapid cycle times, and energy-efficient operation. The robust construction of the press ensures durability and reliability, minimizing downtime. At Wild Tool, the production process begins with raw materials carefully selected for durability and performance. These materials are shaped, heat-treated, and precision machined to create signature pliers, punches, chisels, pry bars, and scrapers. Advanced forging and grinding techniques ensure consistent quality, while strict inspections at every stage maintain exacting standards. Once formed, each tool undergoes surface finishing, assembly, and rigorous testing to ensure functionality and safety. The entire process, from material sourcing to packaging, is completed in-house at Hiawatha, Kansas facility. This commitment to craftsmanship and control ensures that every tool meets the professional grade expectations of the customers. The Bender SP1250 expanded metal production line represents the latest in advanced manufacturing technology for expanded metal mesh. This sophisticated system includes several key components: the AW1250 decoiler, the SP1250 automatic expanded metal production machine, the FLW1250 F flattening and leveling machine, and the O1250 recoiler. Together, they ensure top-level precision across working widths ranging from 250 to 3,100 millimeters, delivering consistent and high-quality results. Key features of the sulfur monophosphide series machines set them apart in the industry. The patented roller gripper infeed system reduces scrap during sheet production without compromising the ability to process coils. For manufacturers seeking enhanced efficiency, the twin system allows the simultaneous production of two stripes with identical specifications, guided in parallel. Additionally, the integrated inline video measuring system provides precision monitoring for fine mesh products, ensuring consistent quality during production. Customization options such as the flexible placement of control units and adjustable cable outlet positions further enhance operational versatility. Beyond the core line, Bender offers a wide range of extensions and accessories to optimize production processes. These include flat rollers, straightening machines, slitting and cross-cutting systems, multi-cut shears, and advanced measuring systems. Winders and unwinders, fully compatible with the sulfur monophosphide series, streamline material handling and ensure seamless operation. The Bender SP1250 line is a robust, customizable solution for manufacturers looking to improve the precision, efficiency, and quality of their expanded metal production processes. The creation of a corrugated elbow begins with preparing a 0.4 mm metal sheet with a diameter of 100 mm. A conical sleeve is inserted into the material, leaving approximately 70 to 80 mm of the metal exposed. This setup allows for easier manipulation during the forming process. The forming involves rotating the sleeve 2 full turns in each direction while applying consistent pressure. Around 7 bends are typically required to achieve an angle of approximately 120 degrees. Maintaining uniform pressure is critical to ensure smooth and even bends throughout the process. Occasionally, the seam may separate slightly during bending. This can be corrected by gently tapping it with a hammer to realign the edges. The material remains straight and free from deformation when handled carefully. For colored materials, minor scratches along the seam may occur. Adjusting the diameter for a more precise fit helps to minimize these marks. Using a 0.4 mm polyester-coated steel, additional precautions, such as rounding all edges, can further prevent scratches. Though this step requires additional effort, it improves the overall quality of the finished product. The result is a neatly formed, functional corrugated elbow. This method can be adapted for various materials with minor adjustments for optimal results. The Gradall tire sidewall cutter is a robust and efficient addition to the Gradall tire processing range, designed to deliver an effective solution for sidewall cutting while ensuring operator safety and ease of use. Built with high-quality components and meticulous in-house engineering, this machine guarantees years of reliable, trouble-free service. The process begins with tires being brought to the machine. Once positioned, the sidewall cutter picks up the tire and uses a durable tool steel-grade cutting blade to slice through the sidewalls, one side at a time. After cutting, the machine deposits the processed tire back onto the ground. This eliminates the need for manual lifting, significantly reducing the risk of back injuries. The operator's safety is further assured through protective safety guards, minimizing the chance of accidental injury during operation. For large agricultural tires, the machine demonstrates its versatility and power. These tires are rolled to the cutter, with 2 people typically managing the task for larger sizes. The cutter then lifts the tire to the blade, where adjustments can be made to determine the size of the cut. Despite the tire's size or shape, the sidewall cutter performs seamlessly, completing the task in under 120 seconds. This machine is designed to process a wide variety of tires, effortlessly handling different sizes and shapes. When paired with the Gradall tire shear, the sidewall cutter enhances tire processing efficiency, offering an unparalleled solution for managing end-of-life tires. The fully automatic 3-phase Stator production line is designed for high-efficiency manufacturing of stator coils for devices like washing machine motors and table fan motors. This line features state-of-the-art automation, offering precision, speed, and reliability. Key components of the line include an AC servo motor system, which powers critical processes like winding, mold dipping, indexing, wire hooking and cutting, and paper feeding. The turntable indexing mechanism utilizes a 3-phase variable frequency reduction motor, ensuring smooth and controlled rotation. This advanced setup enables 3-layer coil winding to be executed simultaneously by 3 individual stations. The spindle is driven by a servo motor, guaranteeing winding accuracy within plus or minus 1 turn. Operational parameters such as working speed are customizable, ensuring minimal vibration and noise. The machine supports parallel winding of 2 wires, providing neat coil arrangements without damaging the enameled wires. An automatic stop mechanism activates when the wire is finished. Wire hooking and cutting are performed by an XY axis servo motion system, enabling precise adjustment of bridge wire and lead wire lengths. The mold dipping process is also servo-controlled, offering consistent and repeatable results. Process parameters for each stator can be individually set and stored via the HMI. Additional features include a cam divider for coil inserting, wedge insertion using mylar, and servo-controlled paper feeding for customizable wedge lengths and intervals. The machine incorporates fault diagnosis, wire brake protection, and pre-deceleration functions for critical mechanisms like winding, wedge making, and coil inserting. Cycle time for single stator coil insertion is less than or equal to 32 seconds per piece, with all operations ensuring zero damage to the wires and wedges. This line represents an integration of precision engineering and automation, making it a reliable solution for high-volume stator production. The class renewal process for the Neptune the Lysis, ARORO cargo vessel owned by Neptune Lines, was executed at Odessa's ship repair yard in Varna, Bulgaria. This critical maintenance ensured the vessel met stringent class standards and remained in optimal operational condition. The renewal began with extensive hull treatment, involving high-pressure and low-pressure freshwater washing across 36,000 square meters, grit blasting over 2,100 square meters, and the application of epoxy primer and silicone coatings on 11,615 and 5,465 square meters, respectively. These steps enhanced the hull's durability and resistance to marine conditions. Specialized protection measures were implemented for vital components, including propellers, ICCP anodes, and thruster propellers. Mechanical inspections and adjustments played a vital role in the renewal. Propeller and bow thruster polishing ensured optimal hydrodynamic performance, while the sea chest gratings were disassembled, cleaned, and painted. The anchor system, including chains and chain lockers, underwent thorough maintenance. Measurements of the propeller rudder system were taken to confirm alignment and functionality. Structural integrity was reinforced through steelwork, which involved replacing thin shell plates and repairing the aft ramp. Pipe systems critical to vessel operations were renewed, enhancing reliability. Deck equipment, such as lifeboats and davits, was refitted and certified, ensuring compliance with safety regulations. The class renewal also encompassed electrical and machinery overhauls, focusing on essential systems like the stern and quarter ramp water hoses, which were serviced and rigorously tested. This comprehensive renewal process not only restored the Neptune the Lysis to peak operational standards but also underscored Odessa's ship repair yard's commitment to precision and quality. The project highlights their expertise in extending the operational lifespan of vessels through maintenance and upgrades.